All right, line Y3, learning task 2, we're going to go and talk about DC shunt types of motors that we're going to have over here. A shunt motor simply means that it is going to be a motor that has only got two parts. It's going to go and have my armature, which is going to go and be the rotating part, and it's going to go and have a shunt field, which is going to be an external field made up of many small turns of wire. Has many turns, and it's going to go and have a fairly high value of resistance due to the fact that it is going to be small turns of wire. And once again, if you go to the very beginning of your generator section, you can take a look. There's a cutaway picture in there where they show the construction of DC machines, and they show cutaway of the windings. You can tell which are your series and which are your shunt just by the size of the wire gauge and the number of turns that are going to be inside of there. Let's go and take a look at these things as far as our standards go. The first thing that we're going to take a look at is direction of rotation when we're dealing with our NEMA subscripts. Now, NEMA subscripts are used to establish standard field connections. This is the North American National Equipment Manufacturers Association, and it is designed to be a standard so that anybody can hook up anybody else's piece of equipment, and we're going to know what exactly those components are going to go and be. We did have a convention of A1 negative for clockwise rotation of a DC generator. We saw that before, where if this was my generator, we'll just circle that one, that's the genset, that if I had my A1 that was going to go and be negative, then that I was going to go and have clockwise rotation of my DC shunt generator that I was going to go and have. If we go and take a look at a motor, we can go and take a look at our A1 negative over here, my A1 negative over here, and we would see that we would also be able to go and have clockwise rotation inside of there, provided that I'm going to be feeding current into my F2. Just take a look at these ones, for what we're looking at off of these two. The big things to go and note are the fact that my direction of current through the windings that I'm going to go and have, not through the armature, but through the actual windings, is going to go and be the same for both of these. On the DC shunt generator, we're going to be supplying that current from the armature, and then it travels through from 2 to 1 and back up to the generator. On my shunt motor, it is going to go and travel from 2 to 1 and back out onto my line that I'm going to go and have over there. If I take a look at my direction of current that I'm going to go and have going through my armature over here, I see that my armature in this case is going to be a load, right? If we're looking at a motor, therefore I'm going to go and have current that is passing through from 1 over to 2 in this direction over here because it is a load. If I take a look at this one over here, I'm going to go and have current that is passing through from 2 to 1, going in the opposite direction, because at that point it is going to be a source. And we know that there's these laws that we have that say that, look, if we have got a source versus a load, current through a source flows from positive to negative. Current through a load flows from negative to positive. When I go and examine these two and the polarities that they are going to go and put out, I see that my A1 and my F2 are connected to the same. In this case, this is going to go and have to be the negative because it is going to flow through a source by armature from positive to negative. In this case, this A1 and F2 over here is going to go and be negative here as well. This is going to be positive over here as well. What they're showing in the picture is the fact that whether we have this machine connected to a prime mover and rotating, or whether we have it connected to lines to go and cause rotation, it's going to be the same connections dealing with the same type of rotation. I would not have to do any changes at all if I wanted to go and take that generator and operate it as a motor, because it's going to be the supply that is going to go and drive the current through in the opposite direction instead of this one over here where this is the supply and driving it through in the opposite direction. All right, looking at direction of reversing my rotation. Direction of rotation can be reversed at any point just by changing around my direction of field flux that I'm going to go and have. We could change the direction inside of our armature, or we can change it inside of the field. It really would not matter which one. I want you to take your right hand right now. I want you to go and form that 3-digit thing that we have for our right-hand motor rule. Your thumb is the thrust, the first finger is the field, the center finger is going to be the current. And because we're looking at the motor rule, we are going to fold that thumb in for the time being because the thrust is the very last thing that we established. Now with your right hand, you should just have your first finger and your middle finger that are going to be out. If you go and take a look at your middle finger, I want you to now just rotate your hand so that your first finger is pointing in the same direction, but your middle finger has changed directions. Got that? First finger in the same direction, middle finger in different directions. Now flip out your thumb. It's going to be awkward because your hand's going to be upside down. But you should see that now your thrust is going down, whereas before your thrust was going up. Reversal of direction of my current through that armature is going to go and reverse the direction of the thrust that I am going to go and have on that motor. We don't have to worry about things like residual magnetism, because residual magnetism was where we were going to go and self-build all of our generator voltage. In this case, we're applying current to it, so whether or not there is any residual magnetism won't make any difference, because we will be sending current through over here and then sending current through over here. These are two complete circuit paths that are both acting as loads to my source. Source is not shown in this case. Over here, I see that I'm once again going and sending through my current on my field from my 2 to my 1. This is going to be a constant that always on my field, I'm going to go from a 2 to a 1. What I can do is I can go and change my armature now, which is different. If you compare this armature over here, now I'm sending my current through from my 2 to my 1 in my armature, which is different than this one here where I was sending it from my 1 to the 2. Because I reversed the direction of current through the armature, my direction of rotation is also going to go and change out of that motor. They show you terminal boxes that are going to go and show these connections where they have gone and reversed that armature. Note that if that armature was not reversed, that my connections would look like, just go and cross that out like that. If the armature was not reversed, the connections would just be straight down like that. L1 to F1 to A2 to A1. That would give me my standard clockwise direction of rotation. And if I want to go and interchange that direction or change that rotation, I just have to go and change the connection on my A2 over here. I've got the option of either changing the direction of current through my field winding, or I've got the option of changing it through my armature. The default in the field is always to reverse something by changing the armature. We don't screw around with the field. The field is just going to go and stay there constant. I like all of my fields to be the same, so does every other electrician that's out there that's ever worked with DC machines, as rare as these things are getting to become at this point. Keep the fields the same, just interchange your direction on your actual armature. What happens if I reverse the lines? Will that go and change the direction? Well, if I reverse the lines, it's going to be doing two things. It's going to be reversing the direction of current through the armature. So now I've got a negative up here, so I'm going to feed through there. But it's also simultaneously going to be reversing the direction that is going through my field. And because I have flipped both of them around, I'm going to go and end up with the same thrust. I want you to start with your right-hand rule right now. I want you to go and have your first finger pointing away from you, your thumb going up in the air, and your center finger, your middle finger, would be pointing off towards the left. That's showing what's happening right now. Now what I want you to do is I want you to somehow reverse that hand and point the finger down, so to speak, back at yourself. You should see that now you have reversed the direction of your first finger, so it's pointing back towards yourself. You should see that then your middle finger is now pointing off towards the right-hand side. It's in the opposite direction as well. That's going to be your current through the armature. And you should see that your thumb is still in the same direction. You get the same thrust. We're seeing all of that illustrated on this, because this over here is going to be my field, my first finger. This over here is going to be my center finger, my armature. This over here is going to be my thumb, or my thrust. And we see the thrust stays constant if I change both of these at the same time. So interchanging the lines on any type of a DC motor is not going to go and change the direction of our motor, because it changes the field and the armature simultaneously. Let's talk about speed regulation and control off of these things here. Speed regulation and control is going to be accomplished based upon a couple of our rules that we've looked at before. Now, we've had a couple of rules. One of them was that we looked at the voltage drop that we have, or the volts over top of our armature, is going to be equal to my applied. So my armature is going to be equal to my E applied minus my EG, the generator voltage or my counter EMF that I build up inside of that motor. We've got that one over there. We've also got this other one that said that EG is going to be equal to K phi and N. This is going to be my counter EMF that I'm going to go and have inside of that motor that is going to be built off of K, which is going to be a machine constant based upon the construction of that machine. Phi, which is going to go and be the amount of flux that I'm going to go and have inside of there, and N, which is going to be my, I'm completely blanked out here on my N for a second. Okay. Oh, my speed that I am rotating that motor at inside of there. Sometimes I forget that I can reapply the speed back in on that one. Anyways, if I go and take all of those, I can put them together. I can combine this one up into here, this volts armature. I can split down into my I armature times my R armature. And then I can go and combine the whole thing to go and form this new formula that you see over there, which is going to go and be N is equal to my E applied, so my source voltage, minus my I A times my RA. All over top of K phi. It's just algebra to go and bring them all together. Of these, we're going to have a couple of these things that are going to go and stay constant. We're going to go and have, I'm going to stick boxes around them. My applied value voltage is going to go and stay constant. My resistance of my armature is going to go and stay constant. It's going to be just what it's made out of, etc. My K, the type of machine, is going to go and stay constant. And my phi is also going to go and stay constant off of that one. And so what I'm going to see is I'm going to see that I'm going to go and have a relationship now that is really going to be based upon my amount of current and my speed over here. What we're going to go and have is as our load goes up, so the actual load, the physical load goes up on there, our physical load is going to go and cause a small drop in my N, my actual speed, which is then going to go and cause this thing to go and have an increase in my current over here. The only way that we could balance this equation, if N was going down, would be for us to go and deal with this I over here. We could go and vary this one here to go and adjust that N value that we have inside it. When we would go and do so, we would see that we're going to start to go and get counterbalancing that's going to go and happen inside of here. Now, all of that's just a bunch of math that we don't need to really look at as much as we need to look at this actual graph that we're going to go and show over here. This graph shows what it is like from no load all the way up to full load, rated load that we're going to go and have on that shunt type of motor. It also goes and relates the speed that I'm going to go and have. Now we see that as I load this thing up, my I is going to be going up. My amount of load current is going to be going up because my motor is always only going to be developing a sufficient amount of torque to overcome whatever is fighting against it. That's all that they ever do. So when we up it, it just takes in more current so that I can go and continue to go and do so. We get this thing all the way up to our load current. What's happened is we have gotten that thing up to our load current, which means that my speed is going to have dropped. It's going to have dropped only a relatively small amount compared to where this thing went and started out. What we would say is that this is more or less going to go and be a constant speed type of motor. There is a small drop, however, it's so small that it's not really going to be much of an issue for us. We like this, relatively constant speed. What we also like is we like the fact that we can adjust that speed so that not only can we be at this rated speed over here, but we can actually curve this in the opposite sort of direction. And the way that we can go and curve it in the opposite direction is if we go and change the amount of flux that we are going to go and have inside of our circuit. If we go and control the field, because the field is going to be related to this. Now we're going back to that same formula over there that my N is going to be equal to my applied value of voltage, E applied, minus my armature, or my armature voltage. I'm just going to stick this E arm over here, all over top of K and phi. If I were to go and drop the phi, which is going to be my field flux, do that right over here. What we would see would be happening is that my N would be increasing in a corresponding manner. And although we don't have necessarily as strong of a field flux, there's still going to be a sufficient amount of residual magnetism, plus it is going to go and self-generate a little bit as each of these windings go whipping past those poles. So it's going to be able to sustain itself. And I'm going to go and have, with that drop in field flux, I'm going to go and have an increase in speed above my base speed. And I can actually go and continue to increase that resistance in the field. Let's just go back to one of these over here. We'll pick this one over here. Let me just erase a few lines here. Let's say that this was the motor that I had. I can go and have a little bit of resistance in there, which is going to go and take me above base speed. I can have a bit more resistance. I can have a bit more, etc. What is the largest value of resistance that you can think of? Well, the largest value of resistance you should be able to think of is going to be a open that we would have. So if I manage to go and open this field circuit while this thing is in operation, I'm going to go and have a maximum value of my, I'm going to have a maximum value of resistance, which is going to result in a minimum value of flux over here. My flux is going to have dropped down, which means I'm going to end up at a maximum value of speed. You have to be very, very careful anytime that you are working with any of these shunt motors. If it only has a shunt field, if that shunt field would be lost, would become open somehow or shut off, what's going to happen is that motor is going to go and increase its speed to dangerous types of speeds. Not generally speaking, if it's got a lot of load attachment, usually the load will go and tap that down, but if this thing is sitting unloaded or lightly loaded, it can go and accelerate to incredibly dangerous speeds, and we call this thing runaway. What we'll do later on is we're going to find out about a bunch of DC motor controls. Those DC motor controls, we're going to go and place them in, so we're going to monitor the speed that we have here, or we can go and monitor the currents that we would go and have traveling through here. Either one of those we're going to be looking for so that we can go and shut down that motor. It's not going to be that we're always going to want to go above base speed. In a lot of situations, what we want to do is we want to go below base speed. And the way to go below base speed would be for me to go and increase this value of resistance over here. If I were to go and increase this value of resistance, what's going to happen is I'm going to drop my value of speed on that motor, which would mean that for this one over here, we would then start operating below what we call rated base speed. Now, the problem with that is if I'm dropping some of those volts across there is that this resistor is going to start to go and heat up. It's going to cause a lot of extra heat that I don't necessarily want to have to go and deal with. So what we will do in a lot of cases, and we won't go and use resistors inside there, we will go and use solid state electronics. Let's just go put in this handy little SCR over here to go and control what's actually going on. As long as we feed this thing with a pulsating type of DC, that pulsating type of DC, we are then going to be able to go and take directly. It's going to commutate. We can go and choose how much that waveform we place through here. All right, torque characteristics of a shunt motor. If we keep our excitation, that's going to be the amount of flux constant, then the torque is going to vary directly or in a linear manner with my armature current. So in other words, if I keep this circuit constant, so I've always got the same amount of current going through there, and if I just go and vary the amount of current that I've got going through the armature, this green path that I have over here, then I'm going to be able to go and have a torque that is going to go and be a linear value. Very little armature current, then it's going to have very little torque. More armature current to go and fight against those field lines and get expelled out. We're then going to go and have more torque out of this thing. Starting torque for these is relatively low, 2, maybe 3 times the full load torque, and it's not going to be great if we have to go and start up, massive inertia loads. Sometimes we really, really like the shunt motors for the fact that we have a relatively constant value of speed out of them, but they won't be able to start the motor or start the load. So we will actually have systems sometimes where we're going to have pony motors that are going to be attached. It's just going to be smaller. Secondary motor that's going to help get the thing moving, and then we shut the pony motor off and we just leave the main motor running, the shunt motor. We'll use these mostly for constant speed. They talk about, drives for paper machines. You got to think about, rolling up massive reels of newsprint. It's relatively rare, but I had a brother that worked out in Port Alberni in one of those paper mills. They monitor that speed so carefully because if, the speed that the paper is feeding off the line is slightly different than the speed that it's rolling up on the drum, and especially if the drum increases in diameter, it's going to go and tear that off. And then, you ruin a whole roll of newsprint, lose money, etc. They got to repulp it. So anything that's going to have to be a really, really constant type of speed, we will do with these DC shunt motors over here. Some of the other ones that they give in here, drill presses, printing presses, lathes, motor jam sets and stuff, aren't as, critical. We can use a lot of other types of motors, but we could see these in there as well. They will not go and start under heavy load applications. So if we need to get a lot of torque to go and start something up, like what we need for our locomotives and mining, we're not going to be using these. We will be using the next motor we're going to look at, which is going to be our series motor.